Okay, so this lesson is going to be on T-formula, when to use it, how to use it, and we'll look at some different scenarios. The idea is, this lesson is kind of a trial. I know we've already covered T-formula, but a lot of you weren't there for that lesson, and it comes up so frequently in HSC that I really think it's something we need to make sure we can all do and all do well. But again, the main reason for this particular lesson is because I'm trialing a format. So I want to hear back from you guys either in the comments of this video on YouTube or back in Canvas on whether you find this useful, whether you'd like to see things done differently. So we're going to go through this lesson and we'll see how effective this actually is for us learning. And if we do like it, next week I'll probably do similar videos for new content so that we can keep on going to the course and not fall behind. All right, so here we go, T-formula. What is it used for? Well, predominantly, we're going to be using it to solve trig equations, that have more than one trig function. For example, here's some scenarios here. Sin x plus cos x is equal to 1, cos x minus sin x is equal to 1, or, tan x plus sin x is equal to 0. That last one, actually, I'd probably just factorize out as sin x. You could use it, solve that one using other methods, but T-formula would work for it. But yeah, predominantly we go to T-formula when our normal techniques that we learnt in the advanced course don't work. That is, when you can't get the trig function by itself. So how does it work? Well, the whole idea of it is you turn a normal trig equation into just an algebraic equation. So if you like algebra, or if you're comfortable solving algebraic equations, you're probably going to find T-formula quite easy, and you're going to like it a lot because that's all it does. Just turns a trig equation into an algebraic equation, and these are the results you need. The whole premise for T-formula is we're making this substitution. We're creating this variable called T. We're going to let it equal tan theta on 2. And when you do that, you end up with these different results for sine, cos, and tan. That means when we have our trig equation, we're going to be able to make these substitutions for sine, cos, and tan and get our new algebraic equation to solve. One important thing before we get on to our examples, and that is the 180-degree case. As you guys hopefully know from our trig graph, 90, 180, 270, and 360, that the the tan graph has vertical asymptotes at 90 degrees and 270, right? Hopefully you remember the tan function looked like this. The reason for the vertical asymptotes is because we know, hey, tan theta is sine over cos, and well, ultimately, every time cos ends up equaling 0, we end up being stuck with a vertical asymptote. So, the tan function does not exist at 90 degrees, right? Tan doesn't exist at 90 degrees or 270. Well, with the T-formula, we're making the substitution tan theta on 2 or tan x on 2, whatever the variable happens to be. Well, according to T-formula, in that case, since we're making that substitution, as far as T-formula is concerned, theta on 2 cannot equal 90 degrees or 270 degrees, right? Because tan doesn't exist at those points. That, of course, implies that theta, at least according to T-formula, theta will never be allowed to equal 180 degrees or, the other one we don't really care about so much. It's outside the domain 540 degrees. So we end up with this weird case with T-formula. T-formula will work to solve equations. It'll give you the correct solutions. However, it doesn't consider 180 degrees a valid solution. So what we're going to need to do, and sometimes 180 degrees is a solution to the trig equation. So what we'll need to do is we're just going to need to manually test 180 degrees ourselves, just to see if it's a solution or not. It's the only angle we need to worry about doing this for. T-formula will come up with all the other solutions for us. Okay, so on to our first example. So sine x minus cos x is equal to 1. We want to solve this for all values of x between 0 and 360 degrees. So whenever you want to use your T-formula substitutions, you first need to state what it is you're doing. We're going to let t equal tan x on 2. So once you make that substitution, you can then freely go into your equation and replace sine x with, right, there it is there, cos x is that, tan x is that. You can freely make these substitutions now. So sine x was 2t all over 1 plus t squared, minus cos was 1 minus t squared all over 1 plus t squared, and the whole thing is equal to 1. So we've made our T-formula substitutions, and we're left with just an algebraic equation just to solve like normal. In this case, I'd probably just times everything by 1 plus t squared, leaving us with a 2t minus 1 minus a negative t squared. And over here, timesing this by the 1 plus t squared, well, will give us 1 plus t squared. All right, and from here, well, t squareds on both sides will cancel. We're going to be left with 2t. Take that minus 1 across to the other side. We end up with 2t is equal to 2. Therefore, t is equal to 1. We have solved for t. Now, remembering the equation, we're trying to solve for x. T did not exist. We created t, right? We've got the first step of, well, we've found the solution for t. Now we need to go back to the substitution that we made. Since t is equal to tan x on 2, and we know t is equal to 1, that means tan x on 2 will be equal to 1. And this allows us to solve for x. So when is tan positive? In the first and third quadrants. And what makes tan 1? It is 45 degrees, right? You go shift tan 1, you get your 45 degrees. So we've got two solutions here for x on 2. That'll be 45 degrees in the first quadrant, which is 45 degrees, and 45 degrees in the third quadrant, which would be 225 degrees. Therefore, giving us, if that's what x on 2 is equal to, x will be equal to 90 degrees, and in this case, 450 degrees. But when we're outside the domain there, when you minus that by the 360, funnily enough, you just get 90 degrees, right? So 450 degrees is actually just a duplicate of the 90 degrees. And since it's outside the domain, we can safely ignore it. So T-formula has given us one solution for x, and that is 90 degrees. And if you do plug 90 degrees into the original equation, it actually does work. So, really cool. T-formula, backed us up here. It got us the solution. Now, remember, T-formula, there's one potential solution that T-formula is blind to. So we're going to have to do the manual test of that. So we are going to test ourselves for x is equal to 180 degrees. So we're going to plug 180 degrees into the original equation. Remembering this is the only potential solution you need to do this test for. Plug it into your calculator, press equals, you end up getting 1. 180 degrees did actually work as a solution. Thus, in this case, we are going to have to include 180 degrees as a valid solution. So when we're writing out our final solutions, thus x will be equal to 90 degrees, right? The solution we got from T-formula. Or it could also be 180 degrees, the solution we got from the manual tests, which you always need to do when using T-formula. All right, first one solved. Let's move on to the next. So this one here is slightly harder. We're trying to solve this equation here. Cos x plus root 3 sine theta, I should say cos theta plus root 3 sine theta is equal to 1. The domain's set to the same. Let's go ahead and solve it. So starting off with our substitution. We're going to let tan equal, t equal tan theta on 2 in this case. And that allows us to go ahead and make our substitutions. Cos theta will be 1 minus t squared all over 1 plus t squared plus root 3 times sine theta, which is a 2t all over 1 plus t squared, and the whole thing is equal to 1. Just like we did last time, I'll times everything by 1 plus t squared. That's a 1 there. And go ahead and solve this equation. We're going to end up with, in this case, the t squareds aren't cancelling. They're actually going to combine. I'll move everything over to the right-hand side, right, just to avoid having a negative t squared. So we're going to end up with t squared plus t squared, right? I've taken that minus t squared across to the other side. We end up with 2t squared minus 2 root 3t, and in this case, the 1's cancel. We're left with 0 there. So just moving everything across, we end up with this equation here. It's a quadratic. It's algebraic. We're going to solve it just like normal. And that means factorize if you can. If not, go to quadratic formula. This one does factorize quite nicely, to be honest. We can take a 2t out, leaving us with a t minus root 3. And whole thing is equal to 0. And this will give us our two solutions in this case for t. T is equal to 0, or t is equal to root 3. So we've got two solutions for t here. Let's go back and find what this is going to correlate to in terms of theta, because that's what we're trying to solve for. Since, here it is, t is equal to tan theta on 2, that means tan theta on 2 will be equal to 0, or tan theta on 2 will be equal to root 3. From the first one, this is a boundary value. When is tan 0? And again, if you're not sure, I always get my boundary values from the actual graphs. When is tan 0? At 0, 180, and 360. So, tan theta on 2 is equal to 0. That's going to give us values for theta on 2 of 0, 180, 360. And solving the second one, here we go. Tan is positive. That's in the first and third quadrants. And when is tan root 3? It is 60 degrees. But of course, you could just shift tan root 3 in your calculator to get to 60. So this second one here, we're going to get two solutions from. That is 60 degrees in the first quadrant, which is 60, or 60 degrees in the third quadrant, which would be the 180 plus 60, so 240 degrees. There are solutions for theta on 2. Therefore, theta will be, times in everything by 2, 0 degrees, 360 degrees, 720 degrees, but if you minus 360, it just comes back down to 360. So that's technically a duplicate. We won't need to worry about that. Onto the 60, that'll become 120. And the 240, that will end up becoming a 480 degree angle. But when you minus 360 from it, that actually gives you 120 degrees again. So again, these last two solutions were just both a duplicate. So T formula has given us three solutions here, 0 degrees, 360, and 120. Before we move on to the next question and call this one done, we better go ahead and test the 180. So just do a manual test. Let theta equal 180. Let's see if it works in the original equation. Cos 180 plus root 3 sine 180. Plug that into the calculator, press equals. You end up getting, in this case, a -1 plus 0. It's a -1. So in this case, it didn't work. So, hence, our final solutions for theta will just be the original three the T formula gave us. 0 degrees, 120 degrees, and 360 degrees. Second one solved. And again, these first two examples are very typical HSC difficulty type questions. The third one's a little different. We didn't see a question like this in class because typically when we're solving things like this, you just use your normal trig identities for. And funnily enough, this one could be done the same way as well. We would have to resort to double angle results, but you actually could prove this. However, T-formula, because of the theta on 2's, we can also prove trig expressions like this using T-formula. And I'm going to do this here just to show you how it works. So anytime you want to use your T-formula substitutions, you're going to state what the substitution is, right? In this case, we're going to let T equal tan theta on 2. Okay, so looking at the right-hand side, I'll start with that because it's the easiest. Well, the right-hand side is tan theta on 2, which funnily enough just happens to be T, right? Using our T formula. That is what tan theta on 2 is. It's just T. So the right-hand side is T. Let's move on to the left-hand side. And hopefully we can show that it is also equal to T. So we've got cot theta on 2 minus 2 cot theta is the left-hand side, which of course is 1 over tan theta on 2 minus 2 over tan theta. So we end up with, well, tan theta on 2 is just T. Tan theta is 2T all over 1 minus T squared, right? Where am I getting that from? It's from those three results, right? These are the results you need. We can see tan theta down the bottom there. So bringing this across to the other side, again, just algebra. We're just going to simplify it here. Fraction over a fraction, you guys know what to do with that. Ultimately, you end up with 2 lots of 1 minus T squared all over 2T. These 2's are going to cancel. So you're left with just T on the bottom of both fractions. We know how to minus fractions with a common denominator. We're just going to end up with on top 1, take away a negative T squared, giving us a positive T squared there. 1 take away 1 is 0. So we're left with T squared all over T, which ends up just becoming T, which funnily enough, check it out, boom, boom, is our right-hand side. Therefore, and then you could go ahead and state what it is. You've proved that the left-hand side is equal to the right-hand side, and everything's done. So that's just an example. I just wanted to show you how T-formula could be used to actually prove these things as well. Typically, it's harder and longer than the normal method. Your normal trig identities like sine squared theta plus cos squared theta is equal to 1 and that sort of stuff is easier. And even in this case, you could do it using, your double angle results. This could be solved using the normal methods, but sometimes T-formula can actually be used in these cases and actually make the question easier. All right, final bonus question at the end. So this one here, again, we're back to trig equations. This one could be solved using because it's equal to 0. Whenever you see that, I'm always going to strongly recommend, in this case, you don't need to use T-formula. What I would personally be doing is rewriting tan x as just sine x over cos x. And then from there, you can go ahead and just simplify it. Factorize out the sine x, right? And once you've factorized out that sine x, you can see, hey, this whole thing is equal to 0. That's only going to occur when sine x is equal to 0, or when 1 on cos x plus root 2 is equal to 0. The first one's already really nice, and you can get your solutions for x straight away, 0, 180, and 360. Again, boundary values from the sine graph. This other one, you know, you'd need to rearrange a little bit to get cos x by itself. Do the reciprocal of both sides. And you'd end up with this. And from here, you know, you could get your solutions, right? Sine x, again, with boundary values, always look at the graph. When is sine x going to be 0? Right here at 0, 180, and 360. So we're getting solutions for x of 0 degrees, 180 degrees, and 360 degrees. And from this second one, we've got cos x is equal to minus 1 on root 2. Cos is negative in the second and third quadrants, and 45 degrees is the angle that gives us the 1 on root 2. So we end up with 45 degrees in the second quadrant and 45 degrees in the third quadrant. So just using our normal methods, we didn't need to use T-formula for this one at all, and we were able to get our solutions. That doesn't mean T-formula won't work. It actually will. You can use T-formula on this. I did it earlier on. You end up getting, you know, 60, like it looks a little bit messy, but for T, you end up getting, I think it was 0, and the other one was the square root of 3 plus 2 root 2. It looks kind of messy, or plus or minus that was actually. It looks kind of messy, but when you type it in, you know, this ends up becoming, for x on 2, it was like 67.5 degrees, and when you double it, you know, you end up getting the 135. Like T-formula does work. It does give you all the correct solutions. It just is longer. And if you really want to practice your T-formula on a harder question, you can go ahead and use T-formula for this. You should end up getting the solutions down below. The only note I'll put in, if you do end up having to go at solving this final one with T-formula, the 180 degrees. 180 degrees is a solution here, which T-formula will not give you. Obviously, you'll have to do that one, get that final solution through a manual test. So it is a fun question to do using T-formula, but again, as you just saw here, not required. The normal methods work out a little bit quicker, a little bit nicer. So we're going to leave that here. As you've gone through this video, please, you know, leave a comment either here on YouTube or back on Canvas. Let me know whether you liked the way I'm doing this, whether you want it different, whether you're happy for me to keep going. I'm thinking about redoing the further functions topic in its entirety through videos like this. So anyway, let me know what you think, and best of luck with your T-formula, guys. All right, see ya.